Welcome to Advanced Linear Algebra. Today, we are going to explore a fascinating and deeply powerful concept called the matrix in a dual basis. If you have ever wondered how mathematical transformations can be reversed or how we can trace the value of an output back to its original input, you are in the right place. This idea is not just abstract math, it is the hidden engine behind machine learning and advanced computer science. Let us dive in and build our understanding from the ground up. Before we look at any equations, let us build our intuition. Why does this concept matter? Imagine you run a factory. The process of turning raw metal into a finished car is a forward transformation. Now, imagine financial inspectors who evaluate the final cars and assign them a dollar value. These inspectors live in the dual space, which is just a mathematical term for the world of measurements. If you want to know how much the raw metal was worth before it became a car, you have to work backwards. You take the car's final value and trace it back through the factory's process. This backward tracing is what we call the transpose of the transformation. Now that we understand the factory analogy, let us define our mathematical tools. In any vector space, we have a standard set of reference vectors called a basis. From this, we can create a dual basis. Think of a dual basis as a set of highly specific measuring tapes. Each tape perfectly targets just one reference vector, giving a measurement of 1 for that specific vector and 0 for all others. When we have a rule that changes input vectors into output vectors, the transpose transformation is a rule that works in reverse. It takes a measuring function from the output space and turns it into a measuring function for the input space. Let us look at how this works mathematically. We start with the forward transformation. Suppose we have an input vector space V and an output vector space W. We have a linear transformation T that maps vectors from V to W. This transformation can be represented by a grid of numbers, which we call matrix A. In this formula, V sub j represents a basis vector from the input space and W sub I represents a basis vector from the output space. The symbol A sub ij represents the specific numbers inside our matrix. Conceptually, this equation simply says that when we transform an input vector, the result is a combination of the output vectors, scaled by the numbers in the matrix. If a matrix entry increases, that specific output direction gets a stronger weight. This formula we just saw leads us to an important question. How do we define the backward transformation mathematically? Here we introduce the transpose transformation, written as T superscript T. The variable g is a measuring function from the dual space of the output. The small circle symbol means composition, which is a way of chaining functions together. This formula tells us that applying the backward transformation to a measuring function g is exactly the same as first transforming the vector forward with t and then measuring it with g. Conceptually, it bridges the forward physical movement with the backward measurement. If the forward transformation scales a vector up, the transpose ensures the measuring tape adjusts perfectly to capture that new scale. Now that we have defined the transpose, we need to find its matrix representation. We will call this new backward matrix B. In this equation, G sub j is a basis function from the output dual space, and F sub I is a basis function from the input dual space. The numbers B sub ij are the unknown entries of our new matrix B. Just like the forward matrix told us how to combine output vectors, this backward matrix tells us how to combine input measuring functions. Our goal now is to figure out exactly what these unknown B numbers are and how they relate to our original forward matrix A. If we change the forward process, these B entries must shift to maintain the balance of measurements. Before we prove how to find those unknown entries, let me give you the final powerful theorem. It states that the matrix of the transpose transformation relative to the dual bases is simply the transpose of the original transformations matrix. The symbols beta star and gamma star represent the dual bases. What this means conceptually is incredibly elegant. You do not need to do complicated algebra with measuring functions every time. You just take the original grid of numbers from the forward transformation and flip it along its main diagonal. The rows become columns and the columns become rows. This simple flip perfectly translates the forward physical movement into the backward measurement space. Let us visualize this elegant relationship. Look at the diagram on your screen. The top layer represents the normal world where vectors live. You can see the input space V on the left and the output space W on the right. The arrow pointing right shows the forward transformation, T, governed by matrix A. Now look at the bottom layer. This is the dual world, the space of measurements. Here we have the dual spaces V star and W star. Notice that the arrow for the transpose transformation, T superscript T, points backwards from right to left. The vertical dashed lines show how each space connects to its dual shadow. The matrices A and A transpose act as the dictionaries that translate movements between these two worlds. Before we move on to the proof, let us see this with a concrete example to see how easy it is to use. We are given a transformation T from a 2D plane to another 2D plane. The rule is T of x, y equals x plus 2y, 3x plus 4y. We are asked to find the matrix of the backward transformation relative to the dual basis. Our approach is simple. We will first find the standard forward matrix by plugging in the standard basis vectors 1, 0 and 0, 1. We plug the first vector into our rule and get 1, 3. We plug the second vector in and get 2, 4. These outputs will form the columns of our forward matrix. Now we take our two output vectors and stand them up vertically to form the columns of our transformation matrix. The first column is 1, 3 and the second column is 2, 4. This matrix tells us exactly how to move forward in the standard space. Now, instead of doing complicated algebra with measuring functions, we apply our theorem. The matrix of the transpose transformation in the dual basis is simply the transpose of the matrix we just found. We flip the matrix along its main diagonal. The first row 1, 2 becomes the first column. The second row 3, 4 becomes the second column. This final matrix perfectly describes how the measuring functions are transformed backwards, and we found it with almost zero effort. Let us try a slightly more abstract example. We are given V as the space of polynomials up to degree 2, which has a standard basis of 1, x and x squared. We are given T as the derivative operator, meaning it takes a polynomial and outputs its derivative. We want to find the matrix of its transpose in the dual basis. Our strategy is the same. We will apply the derivative to each basis vector to build the original matrix column by column. We start by taking the derivative of the first basis vector, which is the constant 1. The derivative of a constant is 0, which we write out fully as a linear combination of our basis vectors. 0 times 1 plus 0 times x plus 0 times x squared. Continuing with our strategy, we take the derivative of the second basis vector, which is x. The derivative of x is simply 1. We write this as 1 times 1 plus 0 times x plus 0 times x squared. Next, we take the derivative of the third basis vector, x squared. Using the power rule from calculus, the derivative is 2x. We write this out in terms of our basis as 0 times 1 plus 2 times x plus 0 times x squared. We now have the coefficients needed to build the columns of our forward transformation matrix. Each column represents how a specific basis polynomial changes when we take its derivative. We place the coefficients from our three results into the columns of a matrix. The first column is all zeros. The second column is 1, 0, 0. The third column is 0, 2, 0. This matrix represents the physical act of taking a derivative in our polynomial space. Finally, we apply our theorem to find the matrix in the dual basis. We transpose the matrix by swapping its rows and columns. This new matrix tells us how the evaluation functions shift when we take derivatives. Physically, it tells us how measuring the x term of a derivative relates to measuring the x squared term of the original polynomial. We have successfully found the shadow transformation. Now that we have used this theorem to solve problems, let us understand where it comes from. We are going to prove that the entries of the backward matrix, B subscript kj, are exactly equal to the transposed entries of the forward matrix, A subscript jk. This chunk of the proof is setting up our test. To find the numbers inside matrix B, we need to test both sides of our transpose definition on a specific input vector, V subscript k. We feed V subscript into the left side, which by definition is the same as feeding the transformed vector, T of V subscript k, into the measuring function G subscript j. We then substitute our very first formula for the forward transformation into the measuring function. This sets the stage for us to use the properties of linear functions. Continuing our derivation, we use the fact that g sub j is a linear function. Because of this linearity, it can slide right past the summation symbol and the constants a sub I k to directly measure the output vector w sub I. This brings us to the defining property of a dual basis. The measurement g sub j of w sub I is equal to the Kronecker delta, written as delta sub ji. The Kronecker delta is a mathematical switch. It turns on and equals 1 only when the label I matches the label j, and it turns off and equals 0 for all other combinations. Because it is 0 almost everywhere, every single term in that long sum vanishes into nothing, except for the one specific term where I equals j. This beautifully collapses the complex sum, leaving us with just the single matrix entry A sub jk. For the final step of our proof, we do the exact same testing process on the right side of our equation, which involves the unknown matrix B. We apply the sum of B sub ij times F sub I to our test vector V sub k. The dual basis function F sub I measures the vector V sub k. Just like before, this acts like a Kronecker delta switch that only survives when the index I equals k. All other terms vanish, leaving us with the single entry B sub kj. By setting the results of the left side and right side equal to each other, we arrive at our beautiful conclusion. The entry in the kth row and jth column of our new matrix B is exactly the same as the entry in the jth row and kth column of our original matrix E. Hence, the backward matrix is simply the transpose of the forward matrix. To summarize our journey today, remember these key takeaways. First, every linear transformation between vector spaces has a shadow transformation between their dual spaces, working in reverse. Second, when we represent these transformations as grids of numbers, the shadow transformations grid is simply the original grid flipped on its side. This elegant relationship bridges abstract geometry and practical calculations. It is the hidden engine behind backpropagation in machine learning, allowing networks to trace errors backwards. It also proves the fundamental truth that the number of independent rows in any matrix always equals the number of independent columns. You have now mastered a deeply powerful concept in advanced linear algebra. Great work!